Hello everyone, Thatcher here. In this video, we will be exploring the mathematics of encryption. There will be various concepts discussed in this video. Specifically, this video will be split into the following sections: Introduction to Cryptography and Encryption, Modular Arithmetic, the Caesar cipher, the Extended Euclidean Algorithm, the Reversed Shamir-Adleman Algorithm, or the RSA algorithm, and a summary at the end. Now, allow me to introduce you to cryptography and encryption. What is cryptography? Well, cryptography is the study of encryption. And what is encryption, you ask? Well, encryption, in simpler terms, is the process of encoding some data which can take the form of numbers, texts, etc., so that only authorized users can understand or decrypt them using a secret code or a private key. In more technical terms, encryption is the process of converting plain text into ciphertext. Okay, so that's that, but why is encryption so important to us? Well, we are now living in an era where the internet and digital technologies are inevitable. Most of us have phones, iPads, laptops, TVs, and so on. And I'm willing to bet that most, if not all of them, are connected to the internet and each other in some way. The internet is a wonderful place. It's a place where all computers are interconnected, together providing a vast global system of communication for each one. However, the internet can also be a dangerous place. It's where cybercriminals will feast on digital information like your passwords and files. So, in this video, we will explore the world of encryption by looking at the many different types and the mathematics behind it. Let us now move on to the next section: Modular Arithmetic. Modular arithmetic is a system of arithmetic for integers where we consider the remainder. When we have a quotient of two integers a and b, remember that we consider the remainder, so only integer answers here, we can write this as a equals b multiplied by an integer q plus another integer remainder r. For example, when a is 10 and b is 4, we can write this as 10 equals 4 times 2 plus 2. Hence, we can write this, which reads 10 is congruent to 4 modulo 2. Note that modulo can also be replaced with mod. There are two definitions for the congruence of two integers. Definition number 1. For integers a, b, and positive integer n, a is congruent to b mod n if both a and b leave the same remainder when divided by n. Definition number 2. For integers a, b, and positive integer n, a is congruent to b mod n if the difference between a and b is an integer multiple of n. To better understand modular arithmetic, let us consider an example we are all familiar with: a clock. We all know that there are two different ways to represent time. We have the 12-hour time format and the 24-hour time format. For the 12-hour time format, a day is divided into two periods: AM, meaning before midday, and PM, meaning after midday. Each period is then divided into 12 hours, with numbers ranging from 1 to 12. The 12 is also replaceable by 0. For the 24-hour time format, a day is divided into 24 hours directly, with numbers ranging from 1 to 24. The 24 is also replaceable by 0. Now, when we write 1500 in 24-hour time, we also mean 3 p.m. in 12-hour time. When we write 2023 in 24-hour time, we also mean 8:23 p.m. in 12-hour time. And here, we will mainly be using examples of times after midday, as the representations of time before midday for both time formats are practically the same. The idea behind using 24-hour time comes from addition and modular arithmetic. Let's look at the clock again. Notice how the numbers are wrapped around the clock? Modular arithmetic also has the same logic. For instance, 3 p.m. What's that in 24-hour time? Well, we start from 12, then slowly wrap around the clock until we reach 3. However, that's only 3 a.m., assuming we start from the beginning of the day. Hence, we can extend the wrapping motion until we arrive at 3 again. Using this information, let us look back to our two definitions for the congruence of two integers. Here, we will set A to be 15 because it is 3 p.m. in 24-hour time, B to be 3, which is the 12-hour representation, and N to be 12, since 12 numbers are indicating the hours on the clock. For definition number 1, we can see that when 12 divides 15 and 3, they leave behind the same remainder, which is 3. For definition number 2, we can see that when 3 is subtracted from 15, the result can be represented by 12 multiplied by an integer, in this case 1. Also note that when the congruence relation between two integers a and b are written like this, it is different to a mod b. The first expression means that integers a and b leave the same remainder upon division by n. The second expression simply returns the remainder of a divided by b. For instance, 9 mod 5 would give you 4, since 9 equals 1 times 5 plus 4. Hence, we can also write 9 is congruent to 5 mod 4. Referring back to our two definitions for the congruence of two integers, we can see that 9 and 5, upon division by 4, returns the same remainder, and that the difference between 9 and 5 is a multiple of 4. Now that we better understand modular arithmetic, let us talk about the Caesar cipher. The Caesar cipher is a method of encrypting messages using a shift mechanism. We shall set the upper letters as plaintext and the bottom letters as ciphertext, and we will shift the ciphertext. Currently, A is mapped to A, B to B, C to C, and so on. So when we enter the plaintext into our Caesar cipher, it will display the original message. Now, to better encrypt our message, we can shift the letters to the left or right. And just to be clear, a shift to the left denotes a positive value, and a shift to the right denotes a negative value. Okay, suppose we wanted to encrypt the message hello with a shift of 3 to the left. So we shift the ciphertext 3 places to the left. Using computer science terminology, we shall say that the shift in value is the key, denoted by K. So now we just match each letter in our message and put it through the Caesar cipher. This will return the strand of letters K, H, O, O, and R. And now, if we were to decrypt the strand of letters, we simply shift the ciphertext 3 places to the right. And again, we just match each letter in our message and put it through the Caesar cipher. This will return the word hello. We can see that because there are 26 letters in the alphabet, the modulus equals 26. It's like the 12 numbers on a clock, in which case the modulus is equal to 12. Say we were to label the letters from A to Z with numbers from 1 to 26 respectively. We then pick a letter to start with, say G, which would have the number 7. We pick a key, say 29, then shift the ciphertext that many slots to the left. Obviously, the sum of 7 and 29 is going to be larger than 26. It's equal to 36. But if we take 36 mod 26, we arrive at the letter that corresponds to our original plaintext. And in this case, 36 mod 26 is equal to 10, since 36 is equal to 1 times 26 plus 10. And the letter associated with the number 10 is the letter J. That's the Caesar cipher. Pretty cool, don't you think? We'll also talk about another encryption algorithm later on in the video, To understand that algorithm better, we need to first learn about the extended Euclidean algorithm. The extended Euclidean algorithm is a two-part algorithm. It carries out the Euclidean algorithm and it computes the coefficients of Bézout's identity. A coefficient is a number, usually an integer, that multiplies a variable. For instance, in the polynomial 3x squared plus 4y minus 2, 3 is the coefficient of x, 4 is the coefficient of y, and negative 2 is the constant coefficient. A constant coefficient is a number, usually an integer, that does not multiply a variable. The Euclidean algorithm is an algorithm that allows efficient computation for the greatest common divisor, or GCD, of two integers a and b. The way we write this is just like so. And in case you didn't know, the greatest common divisor of two integers a and b is the largest positive integer that divides both a and b completely. More mathematically speaking, the greatest common divisor of two non-zero integers a and b is the largest positive integer p, which is a divisor of both a and b, such that a equals pu and b equals pv, where p, u, and v are integers. For instance, the GCD of 12 and 28 is 4, since 4 is the largest positive integer that divides both 12 and 28 completely. And it satisfies these conditions. But it would be quite wearisome if you were to try and work out the GCD of, say, 42 and 56 using brute force. Hence, we would need to use the Euclidean algorithm. Here's what we do. First, divide 42 by 56 and calculate the remainder, which is 0 times 56 remainder 42. We then divide 56 by 42 and calculate the remainder, which is 1 times 42 remainder 14. We then divide 42 by 14 and calculate the remainder, which is 3 times 14 remainder 0. Now, since the remainder is 0, this number here, which is 14, is the GCD of 42 and 56. To generalize this procedure, we write this. As you can see, we start with the two numbers a and b, and work out the remainder. We then replace where a was with b, and where b was with the remainder from the previous expression in the sequence. We then replace where b was with the remainder from the initial expression, and where that remainder was with the new remainder from the previous expression. And we repeat this until the remainder is equal to 0, and you are left with the greatest common divisor of the numbers a and b. Now, there's another part to the extended Euclidean algorithm. That is, the part where we compute the coefficients of Bézout's identity, which states that for non-zero integers a and b, there exist integers x and y such that ax plus by equals the GCD of a and b. And in this case, the integers we will be using are 42 and 56. So how do we go about finding x and y? Well, we need to first list out the steps we did for the Euclidean algorithm, like so. By the way, I've color-coded the different terms for better clarity. And now, we just work backwards and make substitutions. Here's what I mean. We start by taking the remainder on the second to last row, which is also the GCD of 42 and 56, and write it in terms of the other numbers in the same row. So, 14 equals 56 minus 1 times 42. Now, we take the remainder from the row above and write it in terms of the other numbers in the same row. So 42 equals 42 minus 0 times 56. Then we substitute this into the equation above, like so. Now we can do some simplifications and write 14 equals negative 1 times 42 plus 1 times 56. And voila, there you go. These two numbers are the coefficients of Bézout's identity x and y. And that, my friends, is the full procedure of the extended Euclidean algorithm. Now we can move on to the fun stuff. the Rivest-Shamir-Adleman, or RSA algorithm for short. There are two parts to the RSA algorithm. We first generate keys, and then we apply the keys to encrypt or decrypt messages. We need to generate two keys, one public and one private. The public key, which is the key publicly displayed to people online, will denote as E. And the private key, which is the key privately kept to ourselves, will denote as D. To choose E, we first choose two prime numbers, P and Q, that we'll keep secret. In this case, we'll use 3 and 17. We then calculate the product of these two primes, which we'll call n. Here, n will be 3 times 17, which is 51. Note that n will be public, since if n was large enough, then finding its prime factors will be difficult. We'll also need to calculate 5n, which is something called the Euler's-Totient function, where 5n is the number of integers between 1 and n inclusive, which we'll call k, in which the GCD of k and n is equal to 1. In other words, the two integers k and n are co-prime. And interestingly, when n is a product of two primes p and q, 5n is just p minus 1 times q minus 1. So, for our example, p minus 1 is 2, and q minus 1 is 16. So, 5n is equal to 2 times 16, which is 32. There are also two conditions for choosing E. 1. E must be less than 5n. 2. E cannot be a factor of or divide 5n. Let's try E equals 13. Well, 13 is less than 5n, and 13 isn't a factor of 5n. So, E can be equal to 13. There is a way we can check if a number is a factor of some other number. That is, we can use the modulo operation. In our case, 32 mod 13 gives you 6, since 32, upon division by 13, leaves a remainder of 6. Note that technically, the public key contains two numbers, E and 5n. Now to choose D, we need DE mod 5n to be equal to 1. So in our case, 13 times D mod 32 must equal 1. To work out D, we can apply the extended Euclidean algorithm. If we think back to Bezout's identity, it states that there exist integers x and y that satisfies this equation, though we replace a and b with e and 5n respectively, which are 13 and 32. So we find the GCD of 13 and 32 first, like so. We can see 1 is the GCD of 13 and 32. Now we just need to work backwards and compute the coefficients of Bezout's identity. Again, same as before, we take the second to last remainder and write it in terms of the other values in the same equation. We then take the remainder above and write it in terms of the other values in that equation above and substitute this in for 6. This will give us this equation. Now, we could take the first remainder and write it in terms of the other values, but that isn't necessary because rewriting 13 as 13 minus 0 times 32 is a bit pointless. Thus, we arrive at this equation, with these two coefficients. And it is this number that is equal to D, since that is the coefficient of E, our public key. So now, flipping back, we can write D equals 5, and our private key consisting of two numbers will be 5 and 32. The second part of the RSA algorithm is to actually encrypt and decrypt messages. There are two different ways to encrypt or decrypt messages. You could use the public key or your private key to do so for each operation. And here, I'll show all of the operations. I've kept the variables and terms up here in the corner so that we can refer back to them if needed. Let us denote the message as M, and suppose M is equal to 6. Remember, you can assign numbers to letters, symbols, or whatever you may like. Now, we shall encrypt m using the public key. What we do is raise m to the power of e, then take that mod n. This is our ciphertext, which we'll denote as C. So in our case, 6 to the power of 13 equals this number, and that number, mod 51, gives us 27. Now, to decrypt m using the private key, we take c to the power of d mod n. This is our plaintext, which is actually just our original message m. So in our case, 27 to the power of 5 equals this number, and that number, mod 51, gives us 6. The other way is to encrypt m using our private key and decrypt m using the public key. Hence, we have these two equations. M to the power of d mod n equals c, and c to the power of e mod n equals m. Again, we can verify using our numbers, and indeed, we get m back after encryption and decryption. To prove that the RSA algorithm works every time, we first write down the equation for the ciphertext C, which is m to the power of e mod n. Then, we write down the equation for m after decrypting using d, which is m to the power of e all to the power of d mod n. Using laws of indices, we can rewrite this as m to the power of ed mod n. Now, we've established previously that ed mod 5n is equal to 1, meaning ed upon division by 5n leaves a remainder of 1. Hence, we can write ed equals j5n plus 1, where j is some integer. Then, by substituting this into the exponent here, we get m to the power of j5n plus 1, which is also equal to m to the power of 5n all to the power of j times m. And Euler's theorem tells us that an integer x raised to the power of 5n mod n is equal to 1. Hence, we can write the previous equation as 1 to the power of j times m mod n is equal to m. As you can see, this is our original message. Here ends the proof. And that, my friends, is the RSA algorithm. To summarize, in this video, we've talked about what encryption does and why it's important, modular arithmetic, the Caesar cipher, the extended Euclidean algorithm, and the RSA algorithm, which is one of the world's best algorithms in computer science and cryptography. As we've seen in this video, mathematics, prime numbers, modular arithmetic, and number theory, all these are integral to encryption and cryptography. I hope you've enjoyed this video. Thank you so much for watching, and have a great day.